is the one in user land, then the arguments are reinterpreted into the following API calls. So you have add cloak, which basically sets up your hidden memory between a start and end range, and this fake start and fake end is the fake memory that you want to hide or hide the actual memory with. And this is copied into your target PID, so you can use local stack for this or whatever, anything that's going to disappear right after the call. It's fine, it's all copied for you. And in addition to that, all the virtual locking and copy on write probing is done for you to deal with that, so you don't have to worry about that either. Removing a cloak is pretty simple, just the range. This will also remove any associated permissions with that cloak. Then you can add allowed code between the start and end instruction pointer ranges and give that instruction pointer range access to a cloaked region. And the code regions don't need to be page aligned. The cloak regions in all cases should be page aligned. They get ANDed off for you and made page aligned, but things can get confusing if you don't also deal with them that way yourself, especially with sizes and such. And removing allowed removes your region, your allowed region. So core usage example. Here's probably what looks to be the most complicated diagram. You have a region of allowed code between A1 and A2 that's granted access to this evil code. You have C1 and C2 being your virtual address range that this evil code lives in, and then you also have your no map, your no cloaked memory that all other code is given access to. So this is actually accomplished with just 3 API calls. You add the cloak between C1 and C2, those are your virtual addresses, and you say that you want to map to 0, you want it null cloaked, you want it to look unmapped. And then you want to add allowed region for C1 to C2 to access C1 to C2. And that creates this arc here, the self-allowed arc. And then you also want to add allowed between A1 and A2 and grant that access to C1 and C2 as well, and that creates this arc here. And then everything else follows this arc and is presented with unmapped memory. So to make things even easier for you, you have these convenience APIs. These basically provide you with a convenient way to inject it, to hide an injected DLL in a process, and therefore get your code into a process, your hidden code into a process in one nice package. It completely closes the DLL, and it will edit the module list for you using the WinXP offsets, so that it'll disappear from like Proc Explorer's DLL lists and so on. The other 2 convenience APIs are read and write hidden out-of-process versions of basically out-of-process decloaking versions of reprocessed memory and write process memory that allow you to modify hidden memory from out of process or from outside, if you know the key, from outside of your allowed range. So yeah, again, these things aren't really a way to circumvent Tron, because again, there's a 64-bit key behind these that a program that you're reverse engineering is not necessarily going to know or be able to guess easily. So race proofing, I said that race conditions are addressed. So how's this done? Well, the primary race is for intra-thread scanning, when you have a scanner running on your own thread. So you have some hidden code, and then right after that's running, primes the TLBs, and then maybe then a job the scanner job gets scheduled immediately after that job, and then is able to use the TLB mappings to view your hidden memory. So you solve this problem by flushing the TLBs from user land before and after your code executes. This prevents your code from being primed with fake data if the scanner runs before you, and prevents you from allowing the scanner to see hidden data if the scanner runs after you. So the other race condition issue is if you have a scanner running on a different thread. You have an inter-thread race. The way that this is done is that we actually pass the NTOS kernel swap context scheduler function. We use one of the librootkit APIs that's provided to modify this to flush the TLB on every switch, whether it's a context switch or a thread switch. So therefore, your other threads will then have to incur the page fault again and prime their TLBs before they touch that memory, just to make sure that a dedicated scanner thread isn't going to be able to grab the TLB mapping and view your hidden memory. So what are the weaknesses in Tron? Hidden code really doesn't run in VMware. I haven't tried AMD's virtualization or Intel's virtualization. That's promising, but the vanilla VMware seems to flush the instruction TLB when it does an IRET. In other words, so when the page fault handler returns from priming the instruction cache, instruction page cache, VMware flushes it and then causes you to incur the page fault again, and you basically enter into a page fault loop when you try and execute hidden code in VMware. It's really sad because it really would be ideal to be able to reverse engineer possibly malicious programs inside VMware without having to worry about them trashing your system. But unfortunately, it's not the case. But maybe virtualization technology will fix this for us. But data hiding does work though, so you can modify data and try and get results that way. So that's still a possibility. The other weakness is breakpoint verification. If the scanner sets a breakpoint, it can install an exception handler. For those of you who are familiar with Unix, there's a signal handler for SIGTRAP, and then if it jumps to the breakpoint, it expects the SIGTRAP or breakpoint exception to run. It has code in there to return its flow back to the proper point. And if the handler doesn't run, it exits or seg faults or something. So if you have a hidden breakpoint there, and you're trying to see if the program is trying to see if a breakpoint is, or if an area of memory is hidden or not, it can try and write a breakpoint, and if it tries to write to it, it'll write to the fake view because it won't have permissions for that, and then try and jump to it. It'll execute code in the hidden view, which won't cause the breakpoint to fire, and then it'll know that, well, this breakpoint didn't fire, control flow is not returning back to its normal path. So it's sort of the inverse of the breakpoint verification, or the debugger detection using breakpoints. So again, this only works if your data actually, or your hidden code actually presents itself as mapped. Null cloaked memory is fine because when the scanner tries to touch it or virtual query it, it's going to say it's not mapped. So there's really nothing it can do in this case. Room for improvement. In addition to weaknesses, there are just some limitations to Tron. It is not SMP safe. There's all sorts of issues with getting the installing the page fault handler on SMP CPUs. You possibly have to program the APIC to get to get this thing to work. I'm not seeing this slide change. Oh well, I'm just going to assume that it changed. So in the case of SMP, yeah, you're going to have to deal with also, in addition to locking these data structures between your CPUs, you have to install these hooks safely into the page file handler atomically. Oh. Yeah, I seem to be. So I lost some audio. Oh well. I'm also having problems with the slide. Finally, the slide changed. Okay. Okay, so room for improvement. Back from the top. Not SMP or hyperthreading safe. The SMP is a big, and hyperthreading and dual core is a big challenge because you have to install a separate page fault handler. For each CPU, and you have to do this atomically so that yours doesn't start running before the other CPUs are installed and get everything out of sync. You also have to deal with the DTLB in dual core and hyperthreading systems being shared between the two CPUs. So you have to set your process affinity and all sorts of other stuff. So that's a big hassle. Big problem. Have I completely dropped? We seem to be having some difficulties. Alright, I'll just continue. The API is not reentrant, so if you try and use Tron from multiple threads, you have to provide your own locking so that you don't end up making concurrent calls to the Tron API calls. It's not 64-bit clean. It's not going to work on 64-bit architectures. There's x86 assembly all over the place, in addition to patch guard needing to be broken. We are losing some connection quality. So optimizations that can also be done. You have to borrow. In order to speed things up, you can try and borrow a bit from the page tables to try and mark if a page is used by Tron or not, to avoid searching your hook tables or every time that there's a page fault. So you can use the proto PTE page bit or the reserve PTE bit for this. If it's not in your page tables, you should be able to safely pass that down or handle it yourself, and to prevent the OS from complaining about any sort of conflict with these bits, as so long as you handle it first if it is yours. And you can also make the hook arrays into hash tables. Right now it's just a linear search on these tables. Yeah, I'm getting only intermittent connectivity here. This seems like it's a bit better. Okay. ADHD. So ADHD is a debugger detection foiler. Basically, it's another rootkit that'll try and hide the presence of a rootkit via some basic techniques. So what are these techniques for debugger detection? This is the first one is this being debugged flag in your process execution block. This is a per process userland data structure that contains this Boolean